Hi, this is the EdExcel A-Level Further Maths Core Pure Mathematics Paper 2, and it's from the October 2020 series. Question number 1. The curve C has equation y equals 31 times by the hyperbolic sine of x minus 2 times by the hyperbolic sine of 2x, where x is a real number, and we have to determine, in terms of natural logarithms, the exact x-coordinates of the stationary points of C. So, because we're talking about stationary points, of course, we would have to differentiate this. So, if we differentiate y, you'd find dy over dx equaling 31 times by the hyperbolic cosine of x minus 4 times by the hyperbolic cosine of 2x. And now, recognizing that hyperbolic cosine of 2x is equal to 2 times by hyperbolic cosine x squared minus 1, you can see here we end up with 31 times by hyperbolic cosine x minus 4 times by 2 times by hyperbolic cosine x squared minus 1, and that's through Euler's rule. So if we tidy this up even more, you can see here we end up with 31 times by hyperbolic cosine x minus 8 times by hyperbolic cosine x squared plus 4. Now, of course, because we're talking about stationary points, that suggests to us that dy over dx is equal to 0. So we need to set this equal to 0. So we've got 31 times by hyperbolic cosine x minus 8 times by hyperbolic cosine x squared plus 4 equals 0. So if we multiply through by minus 1, you can see we end up with 8 times by hyperbolic cosine x squared minus 31 times by hyperbolic cosine x minus 4 equals 0. We can now factorize this. We have 8 times by hyperbolic cosine x plus 1 times by hyperbolic cosine x minus 4. And all of this is equal to 0. So what you can see from here then is hyperbolic cosine x is equal to minus 1/8 and also equal to 4. Now, as by definition hyperbolic cosine x is greater or equal to 1, we can therefore conclude that hyperbolic cosine x equals 4 is the only solution. So now we need to solve for x. So you can see here x is equal to the inverse hyperbolic cosine of 4, and if you go to the formula book and if you scroll down to the section involving the hyperbolics, the definition for inverse hyperbolic cosine x is shown over here. So we're going to be using this. So this is equal to the natural log of 4 plus 4 squared minus 1 square rooted, and of course because here 15 is less than 4, we can always include the minus as well, and that ensures we don't have a natural logarithm of a negative number. So therefore x is equal to the natural log of 4 plus minus square root 15. This is our final answer. Question number 2. In an Argand diagram, the points A and B are represented by the complex numbers -3 plus 2i and 5 minus 4i respectively. The points A and B are the endpoints of a diameter of a circle, and for part A we have to find the equation of C, giving an answer in the form mod of z minus A equals B, where A is belonging to a set of complex numbers and B is a real number. So to do this, if we have A and B which are the endpoints of a diameter, then the center will be the midpoint of A and B. So let's just write that down. The midpoint is the center, so therefore the midpoint that has coordinates -3 plus 5 over 2 and 2 plus -4 over 2. So therefore the midpoint has coordinates 1, -1. And this will be represented by the complex number 1 minus I. So therefore M is represented by the complex number 1 minus I. And what we can do now is sketch the circle. So we have over here our circle C. We've got the points A and B and the midpoint. So what we can now do is find out the radius of this circle. So the radius R, that's equal to, well, we've got 5 take away 1 all squared plus -4 take away -1 all squared, and then we square root all of this. So it turns out the radius is 5. So therefore, what we can say from this is we've got the mod of z minus 1 minus I equaling 5, and therefore the circle C, that can be represented by the mod of z minus 1 plus I equals 5. And now for part B of the question, the circle D with equation mod of z minus 2 minus 3i equals 2 intersects C at the points representing the complex numbers z1 and z2, and we have to find the complex numbers z1 and z2. So for part B, what we know already is C has this equation. And what we can do first of all is write this in Cartesian form. So we replace the z with x plus iy. So we've got C, which is represented by x plus iy, and then we've got the minus 1 plus I, and all of this is equal to 5. So if we gather all the real parts, we've got x minus 1 plus I lots of y plus 1, and obviously we enclose this in mod symbols. This is equal to 5. And we already know what the equation for D is. You can see here, D, that's given by, if we replace the z with x plus iy, we have D, which is given by the mod of x plus iy minus 2 minus 3i, and all of this is equal to 2. And again, if we gather the real and imaginary parts separately, we've got x minus 2 plus I lots of y minus 3 this is equal to 2. So now if we square both sides, you can see here for C we have x minus 1 all squared plus y plus 1 all squared equals 5 squared, which is 25. And over here we end up with x minus 2 all squared plus y minus 3 all squared equals 2 squared, which is 4. So now if we expand this equation, you can see we've got x squared minus 2x plus 1 plus y squared plus 2y plus 1 equals 25. And here we've got x squared minus 4x plus 4 plus y squared minus 6y plus 9 equals 4. And if we tidy this equation up, you can see we end up with x squared plus y squared minus 2x plus 2y equals 23. And if we tidy this equation up, you can see we end up with x squared plus y squared minus 4x minus 6y equals minus 9. If we call this equation 1 and this equation 2, what we can now do is subtract equation 2 from equation 1, and if we do that, x squared minus x squared, that's 0 x squared, y squared minus y squared, that's 0 y squared, minus 2x minus 4x, that's 2x, 2y take away minus 6y, that's 8y, 23 take away minus 9, that's 32. If we divide through by 2, we've got x plus 4y equaling 16, and if we rearrange to make x the subject, you can see x is equal to 16 minus 4y. We'll call this equation number 3. What we can now do is determine the value of y by substituting equation 3 into equation 1. So now if we substitute in 3 into 1, we have here x squared, so we've got 16 minus 4y squared plus y squared minus 2x, so we've got minus 2 lots of 16 minus 4y plus 2y. This is equal to 23. And if we tidy all this up, well, 16 minus 4y all squared, that's 256 minus 128y plus 16y squared. Then here we've got the other y squared, and here we've got minus 32 plus 8y, and then here we've got the 2y. This is equal to 23. And if we tidy all of this up, we end up with 17y squared minus 118y plus 201 equals 0. And if we go to our calculator, we can solve this equation. So if we solve this polynomial of degree 2, we've got 17 minus 118 and 201 for the coefficients of y respectively. So we end up with y equaling 67 over 17 and also 3. Okay? So this is what y is, and what we can now do is find out the corresponding x coordinates. So when y is equal to 67 over 17, what we can now do is substitute back into equation 3. So here we've got x equaling 16 minus 4 lots of 67 over 17, and if we work this out, 16 minus 4 times by 67 over 17, you'd find that to be 4 over 17. And when y is equal to 3, we have x equaling 16 minus 4 lots of 3, which is 4. So we've got the x and y values, and what we can do with this is form the complex numbers z1 and z2. Of course, z is of the form x plus iy, so therefore z1, that's equal to 4 over 17 plus 67 over 17i, and z2, that's equal to 4 plus 3i. So this is our final answer. Question number 3. A scientist is investigating the concentration of antibodies in the bloodstream of a patient following a vaccination. The concentration of antibodies X, measured in micrograms per milliliter of blood, is modelled by the differential equation 100 lots of d squared x over dt squared plus 60 lots of dx over dt plus 13x equals 26, where t is the number of weeks since the vaccination was given, and for part A we have to find the general solution of the differential equation. Well, before we do anything, we need to form the auxiliary equation, and to do that we consider the left hand side over here to help form the coefficients of the quadratic of the auxiliary equation. So for part A, For the auxiliary equation, you can see here we've got 100 m squared plus 60m plus 13 equals 0. And if we solve for m using our calculator, we enter in the coefficients 100, 60 and 13. It turns out we get minus 0.3 plus minus 0.2i. So let's just write that down. We've got minus 0.3 plus minus 0.2i. We've got complex roots, so therefore for the complementary function, that will be equal to e to the power of minus 0.3t lots of a times by the cosine of 0.2t plus b times by the sine of 0.2t. And now for the particular integral, you can see here we've got a constant term, so the particular integral will be of the form x equals p. And if we differentiate this twice, dx over dt, that's equal to 0, and d squared x over dt squared, that's also equal to 0. We now need to substitute these back into this equation here. So we've got 100 lots of 0 plus 60 lots of 0 plus 13 times by p. This is equal to 26, and therefore p is equal to 2. And therefore, for the particular integral, we have x pi equaling 2, and the general solution is the sum of the complementary function and the particular integral. So we can conclude over here, the general solution for x is equal to e to the minus 0.3t times by a times by the cosine of 0.2t plus b times by the sine of 0.2t plus 2. Now for part B of the question, initially there are no antibodies in the bloodstream of the patient, and the concentration of antibodies is estimated to be increasing at 10 micrograms per milliliter per week, and we have to find, according to the model, the maximum concentration of antibodies in the bloodstream of the patient after the vaccination. Well, here we've got initial conditions. The word initially suggests to us t equals 0, and we know already there's no antibodies initially, so x is equal to 0, and the concentration of the antibodies, we've got a rate over here which it's increasing by. So here you can see dx over dt equals 10, and we can use these initial conditions to help form the particular solution. So before we do anything, it might be a good idea to work out what dx over dt is. So if we differentiate what we have over here, of course we'd have to use the product rule to help differentiate this. We have u dash times by v, so we've got minus 0.3 e to the minus 0.3t times by a times by the cosine of 0.2t plus b times by the sine of 0.2t plus u times by v dash, so we add on e to the minus 0.3t, and if we differentiate this bracket, we'll end up with minus 0.2 a times by the sine of 0.2t plus 0.2b times by the cosine of 0.2t. And of course, if we differentiate the two, we'll end up with 0. So if we now use these initial conditions, first condition we've got t equals 0, x equals 0. So if we substitute into this equation here, we've got e to the power of 0 times by a times by the cosine of 0 plus b times by the sine of 0. And then we've got the 2 over here. And all of this is equal to 0. So we've got a plus 2 equals 0. A is equal to minus 2. Now we've also got the other condition, t equals 0, dx over dt equals 10. So now substituting into this equation here, we've got minus 0.3 e to the 0 times by a times by the cosine of 0 plus b times by the sine of 0 plus e to the 0 lots of minus 0.2 a times by the sine of 0 plus 0.2 b times by the cosine of 0. And all of this is equal to 10. So recognizing that the sine of 0 is equal to 0, we've got here minus 0.3 times a. Of course, cosine of 0 is 1. So we've got minus 0.3 times by a. And then we've got 0.2 times by b. And this is equal to 10. And we already know what a is, that's minus 2. So we've got minus 0.3 times minus 2, which is positive 0.6. And then we add on the 0.2b. This is equal to 10. So 0.2b, that's equal to 9.4. b, that's equal to 47. And knowing what a and b are, we can therefore write out our particular solution for x. So therefore, the particular solution for x, that's equal to e to the minus 0.3t times by minus 2 times by the cosine of 0.2t plus 47 times by the sine of 0.2t plus 2. Now if we go back to the question, we have to find the maximum concentration of the antibodies. So what we need to do over here is recognize we first of all need to set dx over dt equal to 0 because we're considering the maximum concentration. So let's just write this down. We have over here dx over dt equals 0. What we can do from this is find out what t is, and once we know what t is, we can substitute this into x over here, which will enable us to find out the, if we go back to the question, this will enable us to find the maximum concentration of antibodies in the bloodstream. So before we do anything else, knowing what a and b are, we can find out what dx over dt is. We simply replace a and b with the values we've just found over here. And if we do that, we have dx over dt. This is equal to, if we substitute back into here, we have minus 0.3 e to the power of minus 0.3t times by minus 2 times by the cosine of 0.2t plus 47 times by the sine of 0.2t, and then we add on e to the minus 0.3t times by 0.4 times by the sine of 0.2t plus 9.4 times by the cosine of 0.2t. So we now need to set all of this equal to 0. So let's just write all this out again and set it equal to 0. We've got dx over dt, which is this. All of this is equal to 0. So what we can now do is simplify all this by collecting like terms. So if we take out the e to the power of minus 0.3t as a common factor, you can see here, in terms of cosines, we've got minus 0.3 times minus 2, that's 0.6, and we've also got the 9.4 as well. So in total we've got 10 cosines of 0.2t's, and in terms of the sines, we've got minus 0.3 times 47, which is 9. If we work this out, actually, we've got minus 0.3 times by 47, which is minus 14.1, and then we've also got this positive 0.4. So it turns out we get over here minus 13.7 times by the sine of 0.2t. And all of this is equal to 0. Now, as e to the minus 0.3t does not equal 0, we've got 10 times by the cosine of 0.2t. So let's just write this out. Minus 13.7 times by the sine of 0.2t. All of this is equal to 0. So from this, we can rearrange. So here we've got 13.7 times by the sine of 0.2t equals 10 times by the cosine of 0.2t. So therefore, the tangent of 0.2t is equal to 100 over 137, because we've got 10 divided by 13.7, which is 100 over 137. So therefore, 0.2t, that's equal to the inverse tangent of this result. So if we work that out, we've got the inverse tangent of 100 over 137, which is 0.6305, etc. And from this, we can actually find out what t is. So if we store this into A, and then if we multiply by 5, this will tell us what t is. So therefore, t is equal to 3.15, etc. weeks. So what we have to do with this is find out what x is. And of course, we know what 0.2t is. We've just worked that out over here. So what we need to do is substitute into the particular solution for x. So if we do that, we've got x equals e to the power of minus 0.3 times by 3.15, etc. multiplied by minus 2 times by the cosine of the 0.6305, etc. plus 47 times by the sine of 0.6305, etc. and then we've got this extra 2. So if we work this out, using our calculator, we've got e to the power of minus 0.3 times by this, times by, if we work the rest out, we've got minus 2 times by the cosine of what we said a was, plus 47 times by the sine of what we said a was, and then we add on the 2. So it turns out here we get 12.1 milligrams per milliliters, and this is to 3 significant figures. And now for part C of the question. A second dose of the vaccine has to be given to try to ensure that it is fully effective. It is only safe to give the second dose of the concentration of antibodies in the bloodstream of the patient is less than 5 micrograms per milliliter, and we have to determine whether, according to the model, it is safe to give the second dose of the vaccine to the patient exactly 10 weeks after the first dose. So what we're doing for part C is seeing what happens when t equals 10. So for part C, when t equals 10, we've got x equals e to the minus 3 times by, we've got minus 0.3 times by 10, which is minus 3. And then we've got, as well, minus 2 times by the cosine of 0.2 times t, so we've got the cosine of 2, plus 47 times by the sine of 2, and then we add on this extra 2. So therefore you can see x, if we work this out, we've got e to the minus 3 times by minus 2 times by the cosine of 2, plus 47 times by the sine of 2, plus this extra 2, we get a value of 4.16, etc. And this is less than the 5 which was mentioned in the question. So therefore, what we can conclude is it would be safe to give the second dose. Question number 4. For part A, we have to use Moivre's theorem to prove that sine 7 theta equals 7 sine theta minus 56 sine cubed theta plus 112 sine theta to the 5 minus 64 sine theta to the 7. So for part A, obviously we have to use Moivre's theorem, and that's shown in the formula book here. We bring the power into the argument. So we have here cos theta plus I times by sine theta to the power of 7. This is equal to cos of 7 theta plus I times by the sine of 7 theta. And now we need to use the binomial expansion to expand the left hand side, and from that we can compare imaginary parts to find out what sine 7 theta is. So if we use the binomial expansion, first of all here you can see we have cos theta to the power of 7 plus 7 choose 1 times by cos theta to the power of 6 times by I sine theta to the power of 1. Then we have 7 choose 2 times by cos theta to the power of 5 times by I sin theta to the power of 2. Next term, we've got 7 choose 3 times by cos theta to the power of 4 times by I sin theta to the power of 3. Next term, we've got 7 choose 4 times by cos theta to the power of 3 times by I sin theta to the power of 4. Next term, we've got 7 choose 5 times by cos theta to the power of 2 times by I sin theta to the power of 5. Next term, we've got 7 choose 6 times by cos theta to the power of 1 times by I sin theta to the power of 6. And final term, we've got I sin theta to the power of 7. So if we tidy all of this up, you can see here we've got cos to the 7 theta, and then next term we've got 7i cos theta to the 6 times by sin theta. Next term here, we've got minus 21 times by cos theta to the 5 times by sin squared theta. Next term, you can see we've got minus 35 I times by cos theta to the 4 times by sin cubed theta. Next term, we've got 35 times by cos cubed theta times by sin theta to the 4. And then next term, we've got 21i times by cos theta squared times by sin theta to the 5. Then we've got minus 7 times by cos theta times by sin theta to the 6. And then we have minus I sin theta to the 7. And now for us to find out what sin 7 theta is, we would have to compare imaginary parts. So now we will compare imaginary parts. And if we do that, you can see here we've got I sin 7 theta equaling 7i cos theta to the 6 times by sin theta. Then we've got minus 35i cos theta to the 4 times sin cubed theta. Then we've got 21i times by cos squared theta times by sin theta to the 5. And then we've got minus I times 7 times I sin theta to the 7. So let's just write down those results. You can see here we've got sin 7 theta equaling 7 cos theta to the 6 times by sin theta minus 35 times by cos theta to the 4 times by sine cubed theta. Then we've got 21 times by cos squared theta times by sine theta to the 5. And then we've got minus sine theta to the 7. Now, if you remember in the question has everything involving sines only. Now, what links sine to cosine is the identity cos squared plus sine squared equals 1. In other words, cos squared is equal to 1 minus sine squared. So, what we can see over here then is we've got 7 times by cos squared theta cubed times by sine theta minus 35 times by cos squared theta squared times by sine cubed theta plus 21 times by cos squared theta times by sine theta to the 5 minus sine theta to the 7. And now we can replace cos squared with 1 minus sine squared. So we've got 7 times by 1 minus sine squared theta cubed times by sine theta. Then we've got minus 35 times by 1 minus sine squared theta times by squared times by sine cubed theta. And then we've got 21 times by 1 minus sine squared theta times by sine theta to the 5 minus sine theta to the 7. So now we need to tidy all of this up. So if we tidy this up, well, here for 1 minus sine squared all to the 3, we can use the binomial expansion. So we've got 7 lots of 1 minus 3 sine squared theta plus 3 sine theta to the 4 minus sine theta to the 6, and then we multiply this by sine theta, and then we've got minus 35 lots of, if we expand this out, we've got 1 minus 2 sine squared theta plus sine theta to the 4, and then we multiply this by sine cubed theta. Next term, we've got 21 multiplied by 1 minus sine squared theta multiplied by sine theta to the 5, and then we've got the minus sine theta to the 7. So now we need to expand and simplify. So here we've got 7 times by 1 times by sine theta, so that's 7 sine theta, and then we've got 7 times by minus 3 times sine squared times by sine, so that's minus 21 sine cubed theta, and then we've got 7 times 3 times sine to the 4 times sine, so we add on 21 times by sine theta to the 5, and then we've got 7 times by minus sine to the 6 times sine, so that's minus 7 times by sine theta to the 7. Next over here we've got minus 35 times 1 times sine cubed, so here we get minus 35 times by sine cubed theta, and then here we've got minus 35 times minus 2 times sine squared times sine cubed, so that's plus 70 times by sine to the 5. And then we've got minus 35 times by sine to the 4 times sine cubed, so that's minus 35 times by sine to the 7 theta. And then here, if we expand these terms out, we've got 21 times 1 times sine to the 5. So we've got 21 times by sine theta to the 5, and then we've got 21 times by minus sine squared times by sine to the 5. So that's minus 21 sine to the 7 theta, and then we've got the minus sine to the 7 theta. So therefore what we can see is sine 7 theta is equal to, if we tidy all this up by collecting like terms, we've got 7 sine theta, and then we've got the minus 21 minus 35, so that's minus 56 sine cubed theta, and then we've got 21 plus 70 plus 21, that's 112. So we've got 112 sine theta to the 5, and then we've got minus 7 minus 35 minus 21 minus 1, so that's minus 64 sine theta to the 7. Call this equation 1, and this is the result which we wanted to show, so let's just write this down as required. For part B of the question, hence find the distinct roots of the equation 1 plus 7x minus 56x cubed plus 112x to the 5 minus 64x to the 7 equals 0, giving your answer to 3 decimal places where appropriate. So we've got this equation here. We'll call this equation equation 2. And what we will do is compare equation 1 with equation 2. Well, what we can do is, if we take this 1 over to the right hand side, so let's just write this down. If we take the 1 over to the right hand side, we have 7x minus 56x cubed plus 112x to the 5 minus 64x to the 7 equals minus 1. We'll call this equation 3. Then hopefully if we compare what we have with equation 1 with equation 3, hopefully here you can see sine 7 theta is equivalent to minus 1, and the other terms, all the terms here, match up with what we have over here in terms of the coefficients. So through comparison, what we can therefore see, if we compare the 7 sine theta with the 7x, you can see that x is equal to sine theta. That should be quite obvious. So we've got x equals sine theta, and we'll call this equation number 4. Now, what we can also see is that when x is equal to 1, you can see here that the x equals 1 satisfies equation 1 and equation 3. So therefore what we can say is x equals 1 is a solution, and that's through inspection. So what we now have then is this, which we found by comparing this with this, and what we also have is sine 7 theta equaling minus 1. And what we can now do is find out what theta is, substitute back into equation 4 to find out the different solutions for x. Now, what we can do is, to find the values of 7 theta, is sketch the graph from 0 to 14 pi. The reason for that is, typically, we sketch the graph of sine from 0 to 2 pi, but because here we've got a 7 theta, 2 pi times by 7 is 14 pi. So from that we can find out what 7 theta is, and then with that we can find out what theta is. So we're going to be solving this in between 0 and 2 pi. And of course, after this, we're going to have repeated solutions. So we now need to sketch the graph. So we've got the graph over here between 0 and 14 pi. So now we can use our calculator to find out where this is all equal to -1. So -1, that's over here. So let's just show that here we've got -1. And you can see we're going to have 1, 2, 3, 4, 5, 6, 7 solutions. Okay? So what we need to do now is use our calculator to help us find out what those 7 solutions are. So on our calculator, we've got the inverse sign of -1. So this is equal to minus pi over 2. And to find out what this value is, we need to add on 2 pi. So here you can see we've got 3 pi over 2. Okay, so let's just show this. Here we've got 3 pi over 2. Find out the next value, we add on 2 pi. So we get 7 pi over 2. So that's from here. So here we get 7 pi over 2. Next one we add on 2 pi. We get 11 pi over 2. So let's just show this. Here we've got 11 pi over 2. Next one, add on 2 pi. We've got 15 pi over 2. So here we've got 15 pi over 2. Next one, add on 2 pi. We get 19 pi over 2. So let's just show that. Over here, we've got 19 pi over 2. Next one, we add on 2 pi. So we get 23 pi over 2. That's over here. And then next one we get, if we add on 2 pi, we get 27 pi over 2. That's over here. Okay. So what does all this mean? Well, what this means then is that 7 theta, that's going to equal 3 pi over 2. It's also going to equal 7 pi over 2, 11 pi over 2. Then we've got 15 pi over 2, 19 pi over 2, 23 pi over 2, and 27 pi over 2. And from this we can find out what theta is. So therefore theta is going to equal 3 pi over 14, 7 pi over 14, 11 pi over 14, 15 pi over 14, 19 pi over 14, 23 pi over 14, and 27 pi over 14, okay? So now what we need to do is substitute these values of theta back into here in equation 4. So therefore what we can see, we've got x equaling, now if we substitute these values in, so grab your calculator, we've got the sine of 3 pi over 14, so that is to 3 decimal places 0.623, and then we've got 7 pi over 14, so that's the 1, which we've already found. Then we've got 11 pi over 14, so that's a repeat of this. Then we've got 15 pi over 14, so that's minus 0.223. And then we've got 19 pi over 14, so that's minus 0.909. Sorry, 901. And then we've got 23 pi over 14, so that's that. And then we've got 27 pi over 14, so we get that, which is a repeat of this. So therefore, these are our 4 solutions to the equation. So these are the only solutions. Okay? Question number 5. For part A, we're given that y is equal to the inverse tangent of x, and assuming the derivative of tan x, we have to prove that dy over dx is equal to 1 over 1 plus x squared. So to do this question for part A, we begin with y equaling the inverse tangent of x, and if we take the tan of both sides, you can see x is equal to the tangent of y. And now if we differentiate both sides, dx over dy, that's equal to sec squared y. And that's a regular result from A-level maths. And we know that sec squared is equal to 1 plus tan squared. So we've got dx over dy equaling 1 plus tan squared y. And therefore, dy over dx, that's equal to 1 over 1 plus tan squared y. And we know that x is equal to tan y, so therefore tan squared y is equal to x squared, so therefore dy over dx, that's equal to 1 over 1 plus x squared, as required. For part B of the question, we're given that f of x is equal to x times by the inverse tangent of 4x, and we have to show that the integral of f of x with respect to x is equal to a times x squared times the tangent of 4x plus bx plus c times by the inverse tangent of 4x plus k, where k is an arbitrary constant and a, b and c are constants to be determined. So to do this, of course, we will have to use integration by parts. So for part B, we will begin by letting I equal the integral of x times by the inverse tangent of 4x with respect to x. And just as a reminder of what the formula is for integration by parts, the integral of u times by v dash with respect to x is equal to u times by v minus the integral of v times by u dash. So let's just box this formula. And what you can hopefully see over here, u will equal the inverse tangent of 4x. And the reason I want to let u equal this, in part A, we've already worked out the derivative of the inverse tangent of x. So through the chain rule, u dash will equal 4 over 1 plus 16 x squared. We've got v, which we need to work out, and v dash we know is x, so v dash is x, so therefore v is equal to 1/2 x squared. And now we can substitute into this formula here. So if we do that, you can see the integral of x times by the inverse tangent of 4x with respect to x, that's equal to u times by v. So we've got 1/2 times by x squared times by the inverse tangent of 4x minus the integral of v times by u dash. So we've got this times by this, and what I will do is take out the half as a constant. So we've got 1/2 lots of the integral of 4x squared over 1 plus 16 x squared dx. And now what we need to do is figure out what this result is. And we can do that by considering the Pythagorean identities. So let's just write this down in a different colour. Let us consider the integral of 4x squared over the 1 plus 16 x squared dx. Now, if we go to the formula book, we have over here the integral of 1 over a squared plus x squared being 1 over a times by the arctangent of x over a. But we don't have an x squared. Instead, we've got something a bit more complicated. We have f of x all squared. So if we think about some Pythagorean identities which we could use, well, because we're not square rooting anything, when we come to think about the substitution, the Pythagorean identity will not involve sine, cosine, or hyperbolic sine or hyperbolic cosine. So let's think about one of the identities, 1 plus tan squared a being equivalent to sec squared a. Hopefully here you can see, matching everything up, the substitution we will make is tan u equaling f of x, which is 4x, because here we've got f of x squared, which is 16x squared, so f of x is equal to 4x, over a, which is 1. So with this, what we can conclude is u is equal to the inverse tangent of 4x, and what we can also conclude is x is equal to the tangent of u over 4. So if we work out what du over dx is, du over dx, well, through the chain rule we've already worked out what du over dx is. That will be 4 over 1 plus 16 x squared. So therefore, dx over du, that's equal to 1 plus 16 x squared over 4. So what we can conclude from here is dx is equal to 1 plus 16x squared over 4 times by du. So if we replace the variables as necessary, we can therefore conclude that the integral of 4x squared over 1 plus 16x squared dx, this is equal to the integral of 4x squared over 1 plus 16x squared multiplied by 1 plus 16x squared over 4 du. And then hopefully here you can see this 4 and this 4 cancel out. This 1 plus 16x squared cancels with this 1 plus 16x squared. So what we're left with, therefore, is the integral of x squared with respect to u. And we already know what x is, that's tan of u over 4. So what we have over here then is the integral of tan of u over 4 all squared du. So this is equal to, well, if I take out the 1 over 4 all squared, that's 1 over 16. So we have 1 over 16 times the integral of tan squared u du. And we can easily integrate this by replacing tan squared u with sec squared u minus 1. So we have over here, if we tidy this up, we've got 1 over 16 times the integral of sec squared u minus 1 du. So if we integrate, what we're left with is 1 over 16 lots of tan u minus u, and what we can do is, knowing that tan u is equal to, if we go back to what we said here, 4x, and knowing that u is equal to the inverse tangent of 4x, we can therefore conclude we have 1 over 16 multiplied by 4x minus the inverse tangent of 4x. And if you want, you can multiply through by the 1 over 16. So 4 times by 1 over 16, that's 1 quarter. So we've got 1 quarter x minus 1 over 16 times by the inverse tangent of 4x. So now with this we can replace everything as necessary. We know what this bit is, we've just worked it out in blue. So therefore we can say I is equal to the 1/2 x squared times by the inverse tangent of 4x, and then we subtract off 1/2 multiplied by this result in blue, the 1 quarter x minus 1 over 16 times by the inverse tangent of 4x plus some constant k. So if we tidy all this up and expand, we can therefore conclude that the integral of x times by the inverse tangent of 4x with respect to x, that's equal to 1/2 x squared times by the inverse tangent of 4x. Now here we have minus 1/2 times by 1/4 x, that's minus 1/8 times by x, and minus 1/2 times by minus 1/16, that's positive 1 over 32 times by the inverse tangent of 4x plus some constant k. Now for part C of the question, hence find in exact form the mean value of f of x over the interval 0 to root 3 over 4. So this is quite straightforward. For part C, the mean value, that's equal to 1 over root 3 over 4 minus 0, lots of the integral from 0 to root 3 over 4 of x times by the inverse tangent of 4x with respect to x. So now we need to tidy all of this up. Well, we've already worked out what this integral is. So here, 1 over root 3 over 4, that's 4 over root 3. So we've got 4 over root 3 multiplied by this result over here. So we've got 1/2 x squared times by the inverse tangent of 4x minus 1/8 x plus 1 over 32 times by the inverse tangent of 4x, and we're going to evaluate this between 0 and root 3 over 4. So now we need to substitute in all our values. So for the upper limit, we've got 4 over root 3 multiplied by, well here we've got 1/2 times by x squared, so here we've got root 3 over 4 squared times by 1/2, so that will be 3 over 32. And then the inverse tangent of 4 times by root 3 over 4, well that's the inverse tangent of root 3, which is pi over 3. So we're going to multiply this by pi over 3, and then we've got minus 1/8 times by x. X over here is root 3 over 4, so that's our upper limit. And then we've got 1 over 32 multiplied by, as we just said, pi over 3. So that's what we get for our upper limit. And for the lower limit, we have 4 root 3 multiplied by, well here, we're going to have 0 multiplied by 0 minus 1/8 times by 0 plus 1 over 32 times by 0. Well, happily all of that bracket disappears. So now we need to tidy up all of this. So here, we've got 4 over root 3 multiplied by, well, if we tidy all of this up, the 3's here cancel, we're left with pi over 3. And then we've got the minus root 3 over 8 times by 4, which is 32. And then we've got plus pi over 96. So now we need to tidy all of this up even further. So if we do that, we've got 4 over root 3 multiplied by, if we tidy this up, we've got pi over 24 minus root 3 over 32. And if we tidy this up even further, we can cancel the 4 on the outside with the terms on the inside. So we end up with root 3 over 3 multiplied by pi over 6 minus root 3 over 4. Rather, this is 8 at the bottom. So we can expand this out. So we have root 3 pi over 18 minus root 3 times by root 3 over 24. So what we're left with, if we take out a root 3 over 72 as a common factor, we've got 4 pi minus 3 root 3 as our final answer. Question number 6. We're given this matrix with elements k, 5, 7, 1, 1, 1, 2, 1, minus 1, where k is a constant, and given that k doesn't equal 4, we have to find in terms of k the inverse of the matrix M. Well, before we do anything, I think it will be a good idea to consider the table of signs. We've got plus, minus, plus, minus, plus, minus, plus, minus, plus. Now, the first step when finding the inverse of a 3 by 3, let's just write this down, step 1. That will be to find the determinant. Okay? So we will find the determinant of M. So how do we do this? Well, let's just box this. To find the determinant of M, what we need to do is expand along any particular row or any particular column. I will choose to expand along the first row. So if we expand along the first row, we take a look at the first element, which is k. So we've got the determinant of M. The sign associated with it is a plus. And then we cover up the row containing that k and the column containing that k, and then we take the determinant of what's left over. So you can see what's left over is 1, 1, 1, minus 1. Okay? So that's what we do for that. And then we take a look at the next element, which is the 5. The sign associated with it is a minus. So we have minus 5. And then we cover up the row containing that 5, the column containing that 5, and then we take the determinant of what's left over. So you can see what's left over. We've got 1, 1, 2, minus 1 left over. And then we take a look at the next element. So the next element is 7, and the sign associated with it is a plus. So here we've got plus 7, and then we take the determinant of whatever doesn't contain that column or that row. So we take the determinant of 1, 1, 2, 1. So now what we need to do is work all of this out. So here we've got k lots of minus 1, minus 1, minus 5 lots of, well, here we've got minus 1, minus 2, and then we've got plus 7 lots of 1, minus 2. So working this out, we have minus 2k minus 5 lots of minus 3 plus 7 lots of minus 1. So if we tidy all this up, you can see the determinant is 8 minus 2k. So that's what we do for the first step. For the second step, we have to find the matrix of the minors, and this is quite a lengthy process. So let's just move all of this over here just to save ourselves a bit of room. So for our second step, we will find the matrix of the minors. Okay, so let's just box this. To find the matrix of the minors, we're obviously going to have 9 elements, and what we need to do is, first of all, take a look at the element here. We cover up this column, we cover up this row, and then we take the determinant of what's left over. So what we've got left over, we'll write it out in full actually. We're going to have, if I just draw the lines first, we've got for this top element 1, 1, 1, 1, minus 1. Okay, so that's what we've got for the first one. So let's just fill in these. And then we take a look at this row and this column, we cover them up, and then we take the determinant of what's left over. So you can see what was left over was the 5, 7, 1, minus 1. So then if we take a look at this element, we cover up this row, we cover up this column, we take the determinant of what's left over. What's left over is the 5, 7, 1, 1. So that's the first column completed for the matrix of the minors. Next, we will move on to the second column. So for the second column, let's just fill all these in. So let's just add in our boxes like so. What we do for the next column, we cover up this column, we cover up this row, we take the determinant of what's left over. So you can see what's left over is 1, 1, 2, minus 1. Next, we cover up this row, this column rather, and this row, and then we take the determinant of what's left over. You can see what's left over is k, 7, 2, minus 1. We then cover up this column, this row, we take the determinant of what's left over. What's left over is k, 7, 1, 1. So that's that particular row completed, and now for the final column, let's just add in our lines as so. So if we do that, our next step is to cover up this column, cover up this row, we take the determinant of what's left over. What's left over is the 1, 1, 2, 1. We then cover up this column, we then cover up this row, we take the determinant of what's left over. What's left over is the k, 5, 2, 1. And then finally, we cover up this column, we cover up this row, we take the determinant of what's left over. What's left over is the k 5 1 1. So this over here, which I've just found, is the matrix of the minors. So let's just add a curly bracket around this, like so. Okay, and let's just move this slightly to the right. So here, this is the matrix of the minors A. So now we need to tidy all of this up. So if we do that, you can see here, A is equal to, well, for the one over here, we've got minus 2 minus, sorry, we've got minus 1 minus 1, that's minus 2. Okay, let's just tidy this up a little. And then we've got over here, minus 5 minus 7, that's minus 12. So we've got minus 12 here. And then here we've got minus 5, we've got 5 minus 7, that's minus 2. For the column here, we've got minus 1 minus 2, that's minus 3. So here we've got minus 3. Here we've got minus k minus 14. And then we've got here k minus 7. And then we've got 1 minus 2, that's minus 1. And then we've got k minus 10. And then we've got k minus 5. So this is the matrix of the minors. And now our third step, step 3, will be to find the matrix of the cofactors. So for us to find the matrix of the cofactors, what we need to do is consider this table of signs and apply it to the matrix of the minors. So what we'll do over here is we'll copy and paste this, okay? And what we'll do as well is, let's get rid of these brackets for a second just to expand it out, give ourselves a bit more room. So we're now going to consider the table of signs. So here we've got a plus, here we've got a minus, here we've got a plus, here we've got a minus, here we've got a plus, here we've got a minus, here we've got a plus, here we've got a minus, and here we've got a plus. So this matrix, we'll call it C, is the matrix of the cofactors. So now if we tidy all of this up, you can see here we've got minus 2, 12, minus 2. Then we've got 3, minus k minus 14. So let's just write this out clearly, minus k minus 14. And then we've got here 7 minus k. And then here we've got minus 1, 10 minus k, and k minus 5. So this is the matrix of the cofactors. And now our fourth step, step 4. This is to transpose the matrix of the cofactors. So when we talk about transposing the matrix of the cofactors, what we need to do is swap the rows and columns. So this row becomes our first column, so we've got minus 2, 3, minus 1. This next row becomes our next column, so here we've got 12, minus k, minus 14. And then we've got 10, minus k. And then here, this last row becomes our last column, so here we've got minus 2, 7 minus k, and k minus 5. So this is the transpose of matrix C. So now what we need to do then is find the inverse. So step 5, this is to find the inverse of the matrix. So if we find the inverse of the matrix is equal to 1 over the determinant of M times by C transpose. So here you can see we end up with, well, we've got C transpose over here. We'll just copy and paste this. So here we've got C transpose. So let's just tidy this up a little. And then we've also got 1 over the determinant, and we worked out the determinant in this step. That was 8 minus 2k. So the inverse of the matrix, that's 1 over 8 minus 2k lots of this matrix here. So this is how we find the inverse of a 3 by 3. And you can see it's quite a lengthy process, but I thought I'll show all the steps to make it clearer. So this is the inverse of the 3 by 3 matrix in terms of. For part B of the question, we have to find in terms of P the coordinates of the point where the following planes intersect. So we've got 2x plus 5y plus 7z equals 1, x plus y plus z equals P, and 2x plus y minus z equals 2. And what we can do to begin with is write this system of equations in matrix form, and that is exactly what I've done here. So we've got the matrix 2, 5, 7, 1, 1, 1, 2, 1, minus 1, times by the vector x, y, z. This is equal to the vector 1, p, 2. So now we need to find out what x, y, z is. So x, y, z, this is equal to the inverse of this matrix 2, 5, 7, 1, 1, 1, 2, 1, minus 1, multiplied by 1, p, 2. So now for the inverse of that matrix, we can find this using our calculator. So on our calculator, if we go to the matrix mode, define matrix A with 3 rows, 3 columns, we've got 2, 5, 7, 1, 1, 1, 2, 1, minus 1. So if we load up that matrix and then take the inverse of it, you can see here we've got this matrix here. So what I'm going to do is take out the 1/4 on the outside. So we've got 1/4 lots of, well, here we're going to have minus 2, 12, minus 2, 3, minus 16, 5, minus 1, 8, and minus 3. It just makes things a little tidier. So then we will multiply this by the vector 1, p, 2. So now what we need to do is multiply all this together. So if we do that, we've got 1/4 lots of, well, here we've got minus 2 times by 1, so that's minus 2. Then we've got 12 times by p, so we add on 12 p, and then we've got minus 2 times by 2, that's minus 4, and then we've got 3 times by 1, minus 16 times by p, 5 times by 2, and then we've got minus 1 times by 1, 8 times by p, minus 3 times by 2, that's minus 6. So this is what we get, and now what we need to do is simplify all this. So if we tidy this up, we've got 1/4 lots of, well, here we've got 12p minus 6, here we've got 13 minus 16p, and then we've got 8p minus 7. So that is the inverse, that is what x, y, z is, and it says in the question, find the coordinates. So if we write this in coordinate form, you can see here in conclusion the coordinates will be 12p minus 6 over 4, 13 minus 16p over 4, 8p minus 7 over 4. So that's how we approach that question. For part C of the question, you have to find the value of q for which the following planes intersect in a straight line. We've got 4x plus 5y plus 7z equals 1, x plus y plus z equals q, and 2x plus y minus z equals 2. And for this value of q, we have to determine a vector equation for the line of intersection. So what I've done already is copied out the system of equations. We'll call the first one 1, the second one 2, the third one 3. And we need to find out what q is essentially. So the way we can do that is by eliminating one of the variables. I'm going to choose to eliminate the variable z. Now, what we need to do is multiply this equation 2 by 7, and if I do that, I'm going to get 7x plus 7y plus 7z equals 7q. We'll call this equation 4. And now to eliminate the z's, what I can do is subtract equation 4 from equation 1. Okay, so perhaps if I move all this to the center, what I can do is do equation 4, take away equation 1. So if I do that, subtracting the equations, 7x minus 4x, that's 3x. And then we've got 7y, take away 5y, that's 2y. 7z minus 7z, that's 0z. 7q minus 1, that's 7q minus 1. We'll call this equation 5. And what we can also see is by adding 2 and 3 together, we'll eliminate the z's. So we will do equation 2 plus equation 3. And if we do that, x plus 2x, that's 3x. Y plus y, that's 2y. Q plus 2, that's q plus 2. Call this equation 6. And now for consistency, as you can see on the left hand side of equation 5 and 6, those are the same. So therefore for consistency, we've got 7q minus 1 equals q plus 2. So therefore, q is equal to 1/2. And with q equaling a half, okay, so with q equaling 1/2, you can see that equation 5 and equation 6 become, well, on the left hand side we're still going to have the 3x plus 2y, but on the right hand side we've got here a half plus 2, which is 5 over 2. Okay, and what we'll do as well is so what we've done over here is found out what Q is, and now for the next part we need to find the vector equation where they intersect. So essentially the three planes will intersect with a sheaf, so that makes sense. So the planes form a sheaf, and what we need to do is find out the line where they all intersect. Of course, there's going to be an infinite number of solutions. So the way we can do this is multiplying this equation by 2. So here we're going to have 6x plus 4y equals 5. We'll call this equation 7. And if they form a sheaf, we can therefore conclude that they intersect on a line. Okay, so what we can do over here is with this equation 7, we can rearrange for y. So from equation 7, you can see y is equal to 5 minus 6x over 4. We'll call this equation 8. So we've got y in terms of x. Let's also write z in terms of x. So if we go back to here, you can see by subtracting the equation 3 from equation 2, the y's will cancel. So if we now do equation, well, let's just write this down. We now need to solve z in terms of x. So to do that, what we can do is do equation 3 minus equation 2. So if we do 3 minus 2, so 3 minus 2, we've got 2x take away x, that's just x. And then we've got y take away y, that's 0y, minus z take away z, that's minus 2z. And this is equal to 2 take away q, so that's q, 2 take away a half because q is a half, so that will be 3 over 2. And from this we can see, if we multiply through by 2, we've got 2x minus 4z equals 3. So we need to rearrange for z in terms of x. So if we rearrange, we've got 4z equals 2x minus 3. So therefore, z is equal to 2x minus 3 over 4. We'll call this equation number 9. So because y and z are defined parametrically in terms of x, we can let x be any value, say lambda. Okay, so let's just write this down. So as y and z are in terms of x, we can write the vector line parametrically. So essentially the idea is over here, because there's an infinite number of solutions, we're going to let x equal just a random number, say lambda, and from that we can find out what the corresponding y and z points are. So if we let x equal, say, lambda, then it follows from here y is equal to, so if we go back to our equation for y, that's going to equal 5 minus 6 lambda over 4, and z is equal to 2 lambda minus 3 over 4. So what we're going to do is, well, we'll call this equation number 10. I'm going to call this equation number 11. So what we can do from equation number 10 is rearrange for lambda. And the reason I want to do that is because if you look in the formula book under the vectors section, if we know what lambda is, we can find the Cartesian equation of the vector line. So from equation 10, multiplying through by 4, first of all, we've got 4y equals 5 minus 6 lambda. 6 lambda is equal to 5 minus 4y, and therefore lambda is equal to 5 minus 4y over 6. So therefore lambda is equal to, if we simplify this, we get minus 2/3 y plus 5 over 6. Okay, we'll call this equation number 12. And what we can also do is do a similar thing with equation 11. So from equation 11, we can rearrange for lambda. So we've got 4z equals 2 lambda minus 3. 2 lambda is equal to 4z plus 3. So lambda is equal to 4z plus 3 over 2. So therefore, if we find out what lambda is equal to 2z plus 3 over 2. We'll call this equation 14. Okay? So now that we know what lambda is, we can set equation 12 equal to 14, and this is equal to x. And the reason I want to do that, just to emphasize, what we can do is find out the Cartesian equation, as we see over here. So what we can therefore say is we've got x, which is equal to minus 2/3. Well, let's just write it out in full. So here we've got minus 2/3 y plus 5 over 6, and this is equal to 2z plus 3 over 2. And of course, this is all, well, let's write on a different colour. This is all equal to lambda. So what we can do is rewrite each of these. So here we're going to rewrite this as x minus 0 over 1 equals minus 2y over 3. Let's write out neatly. We have minus 2 over 3y plus 5 over 6, and to get the y by itself, I need to divide everything by minus 2 over 3, and this is equal to 2z plus 3 over 2, and I'm going to divide this entire thing by 2 to get the z by itself. So what this is the same as is x minus 0 over 1. This is equal to y minus, well, here we're going to get 5 over 4 divided by minus 3 over 2, and this is equal to z plus 3 over 4 over 1/2. So what we can see from here, if we match with what we have over here, we can form the vector A and B. So therefore, the vector A is equal to 0i minus 5 over 4j plus 3k, and the vector b, that's equal to I minus 3 over 2j plus 1/2 k, which is the direction vector. So what we can therefore say from here then is r equals 0 minus 5 over 4, 3 over 4, plus lambda, lots of 1 minus 3 over 2 and 1/2. And if you want, you can multiply through by 2 over here, so we don't have any fractions for our direction vector. And of course, because those will be parallel, that's not going to make much difference to our final answer. So we're going to have r equals 0 minus 5 over 4, 3 over 4, plus t, some new parameter because we're multiplying through by 2, and we're going to have 2 minus 3, 1. So you can have any equivalent vector. Question number 7. A student wants to make a plastic chess piece using a 3D printer, and figure 1 shows the central vertical cross-section of the student's design for one chess piece. The plastic chess piece is formed by rotating the region bounded by the y-axis, the x-axis, the line with equation x equals 1, the curve C1 and the curve C2 through 360 degrees about the y-axis. And the point A has coordinates 1, 0.5, so let's just add this to the diagram. We have here 1, 0.5, and B has coordinates 0.5, 2.5. So here we've got 0.5, 2.5, where the units are centimeters, and the curve C1 is modeled by the equation x equals a over y plus b, where y is in between 0.5 and 2.5, and we have to find the values of a and b for part A. So what we can do is simply substitute these coordinates into this equation and then solve simultaneously. So for part A, we begin with the coordinates of 1, 0.5. So we've got 1 equals a over 0.5 plus b. So therefore, we've got 0.5 plus b equals a. So therefore, a minus b is equal to 0.5. We'll call this equation 1. And if we substitute in the 0.5 and the 2.5, we have 0.5 equals a over 2.5 plus b. So if we multiply through by 2.5 plus b, we end up with 1.25 plus 0.5b equals a, from which we can see a minus 0.5b is equal to 1.25. Call this equation 2. So now what we can do is solve equation 1 and 2 simultaneously. So if we do that on our calculator, go to the equation solver, we've got a simultaneous with 2 unknowns, type in the coefficients. So here we've got 1 minus 1, 0.5, and then here we've got 1 minus 0.5, 1.25. So we get 2 and 3 over 2. So we can therefore conclude A is equal to 2 and B is equal to 1.5. And therefore what we can conclude is C1, that will have equation x equals 2 over y plus 1.5. Let's now move on to part B. And for part B of the question, the curve C2 is modelled to be an arc of the circle with centre 0, 3, and use calculus to determine the volume of plastic required to make the chess piece according to the model. So essentially what this is saying is we've got a centre over here with coordinates 0, 3. Okay, so let's just write this closer to the centre. So here we've got 0, 3 for the centre. And with this we can find out what the equation of C2 is. Of course, if you imagine that we've got a full circle, like so, then with this we can find out what C2 is and then integrate using the volume of revolution. So we know what the center is, we can find out what the radius is of this circle. So the radius goes from the center to a point, so let's just call this the radius. So what you can hopefully see here, if we work out the radius, we've got 0.5 squared plus, well, 2.5 take away 3, that's going to be minus 0.5, and then when we square that, we're going to add on another 0.5 squared. So the radius is going to be root 2 over 2. So therefore, the radius will equal, well, let's just add this in a place we can see. The radius is equal to 1 over root 2. So therefore, the equation for C2, we're going to have x squared plus y minus 3 all squared equals r squared, which is 0.5, because we're going to have this value squared. So what we can now do is integrate using the volume of revolution. So if we integrate using the volume of revolution, we're rotating 360 degrees about the y-axis. So the formula we're going to be using is the integral of x squared dy. So what we can do over here is rearrange for x squared. So here, x squared is equal to 0.5 minus y plus y minus 3 all squared. So if I call this equation 3 and this equation 4, what we can do is find out the volume of revolution when we rotate C1, the volume of revolution when we rotate C2, and the volume of revolution when we rotate this bit over here. And notice when we actually come to rotate this bit here, perhaps if we show it like this as the chess piece, hopefully here you can see we're going to end up with a cylinder at the bottom, and then here we've also got the piece over here. So hopefully you can see what this will look like in 3D once we rotate it. So let's call this middle bit V1. So let's just get a different color. So let's call this one V1. We'll call this top one V2, and we'll call this bottom one V3. So if we think about V1, we're going from, in terms of y, from 0.5 to 2.5. So if we use that information, we've got V1, which is equal to pi, lots of the integral. So here, don't forget, sorry, I think I forgot to add it on. Here we got pi, lots of the integral. So here we've got pi, lots of the integral from 0.5 to 2.5 of v1. So we're going to have this value all squared. So let's write it out in full. We've got here the integral from 0.5 to 2.5 of x squared. So here we're going to have 2 over y plus 1.5 squared dy. So squaring the 2 we get 4, so we can take that outside the integral. So we've got 4 pi lots of the integral from 0.5 to 2.5 of 1 over y plus 1.5 all squared dy. So here we get 4 pi lots of the integral from 0.5 to 2.5 of y plus 1.5 to the minus 2 dy. So if we work this out, we're going to have 4 pi lots of minus y plus 1.5 to the minus 1 from 0.5 to 2.5. So now we need to work all of this out. So we've got 4 pi lots of minus 2.5 plus 1.5 to the minus 1 minus 4 pi lots of minus 0.5 plus 1.5 to the minus 1. So if we tidy all of this up, here we've got 4 pi lots of minus, and then here we've got 4. We've got here minus 4 to the minus 1 minus 4 pi lots of minus, well here we're going to get 2 to the minus 1. So here we get pi. Okay, so that is the volume formed by rotating v1. And now we can do a similar thing to find out the volume when we rotate v2. So if you go back to the question, we need to find our limits. Now we're going from b to essentially the top over here. Now this here will have coordinates. Well, if the y coordinate here is 3, we add on the radius to get this top coordinate, which is 3 plus 1 over root 2. Okay, so that's the y coordinate. Of course, the x coordinate is just 0. So when we come to find out what the volume is when we rotate v2, we've got pi lots of the integral from 2.5 to, say, alpha of 0.5 minus y minus 3 all squared dy, where alpha is equal to 3 plus 1 over root 2. Now the only reason I'm writing alpha is because I don't want to continuously write this result out again and again. So if we work all of this out, you can see we've got here pi lots of, now if I integrate the 0.5, I'm going to get 0.5y, and if I integrate y minus 3 all squared, I'm going to get minus the third lots of y minus 3 all cubed. And I'm going to evaluate this from 2.5 to alpha. So the way we can tidy this up is, well, let's substitute in actually. So here for the upper limit, we've got pi lots of 0.5 alpha minus a third lots of alpha minus 3 all cubed. So that's what we get for the upper limit. And then for the lower limit, we're going to have pi lots of 0.5 times by 2.5 minus 1/3 lots of 2.5 minus 3 all cubed. So now we need to work all of this out. So let's work all of this out. For the upper limit, we're going to have pi lots of, well, here we've got 3 plus 1 over root 2, which is this. So here, if we store this into a, we've got 0.5 lots of a, which is this. So here we get 6 plus root 2 over 4. And then here we've got a, take away 3, then cubed, and then we're going to divide this by 3, so then we subtract off root 2 over 12. And then here for the lower limit, we're going to have here, if we work this out, 0.5 times by 2.5, take away 2.5, take away 3, all cubed, divided by 3, which is 31 over 24. So we have 31 over 24. So if we tidy up this first bracket, you can see here we've got 6 plus root 2 over 4, take away root 2 over 12, which is 9 plus root 2 over 6. So here we've got 9 plus root 2 over 6 lots of pi minus 31 over 24 pi. So what we will do is take away 31 over 24. So here you can see we end up with 5 plus 4 root 2 over 24 pi centimeters cubed. Okay, so that's what we get for V2, and then for V3, you can see here, if we go back to the diagram, we've got a cylinder. The radius, now we're going from the center to 1, so the radius is going to be 1, and the height is 0.5. So here, for V3, we're going to have pi r squared times by h, so we've got pi times by 1 squared times by 0.5, which is pi over 2. So therefore, for the total volume, we've got pi, which is what V1 is, plus 5 plus 4 root 2 over 24 pi plus pi over 2. So here we can take out the pi as a common factor. So we've got pi lots of 1 plus 5 plus 4 root 2 over 24 plus 1/2. So if we work this out, so we're going to add on 1, and then we're going to also add on 1/2. So we're going to get this over here. We're going to end up with 41 plus 4 root 2 over 24 pi centimeters cubed. So if we times this by pi, we get 6.11 centimeters cubed. So this is approximately 6.11 centimeters cubed. So that's how we approach this question.